Okay, all right. Well, we will go ahead and get started. Today, we are looking at tidy data and pivoting data. Okay, so just to kind of put everything in context, because we've been covering a whole bunch of stuff in RStudio and R and coding this and that, and you've got data camp and all of this, okay? All of this in the beginning is just giving you the tools for how to work with data, right? Because before we can start asking questions and looking for answers in the data, we just have to learn how to use our tools to interact with the data, right? It's kind of like in cooking. You got to learn how to use a knife. You got to learn how to, use the stove and the oven, and learn the different tools before you can start really kind of creating stuff. So a lot of this is going to be, we're still kind of going into just like what are some of the tools, and then periodically I'll kind of intersperse it with, okay, here are some things you can do, some applications, with the tools that we have. So I think early on we covered visualization, and then I did just a little demo of like, here's some visualizations you can do, okay? And then now that we've covered a few more kind of tools, dplyr with kind of mutating, filtering, summarizing our things, probably either our next lecture or maybe in the following week, I'll do, maybe a slightly more thorough example of how to use some of those tools, including the stuff I covered today, to start, asking questions and answering questions. Okay. I don't know if you have met with your groups yet, but I want to encourage you to just kind of start talking about what kind of data you want to look at. All right, and you should look for different data sets and start kind of going through. Maybe there's a topic you like, and maybe there's multiple topics that you are open to. Look for some data sets related to that. And then once you kind of think you have a data set, again, start looking through it carefully to make sure that the data seems reliable, especially if you're taking it from someplace like Kaggle or someplace where people are uploading and submitting their own data sets. Okay? If you're getting your data set from maybe a government institution that you feel is going to be a little bit more trustworthy, more reliable, then that's fine. But you kind of want to look at what variables are available, and start asking what kind of questions can I even start to answer with the data that we have. So in Monday's lecture we covered how do you even get your data into R, which is going to be very important. And then today we are going to look at how to make your data tidy, and that includes pivoting your data. So there's kind of this this tool that allows us to pivot our data, and I will show you exactly what I mean by that. And when you pivot your data, you can start asking questions and doing comparisons. So let's take a look and see what we can do here. Okay, this is related to the related reading for this chapter is chapter 6 in our textbook, and the idea with tidy data is that every row contains one observational unit. Sometimes we call that a case. Okay, and each observation has its own row. Each observation is one row. So you're not going to have two observations in one row, and you're not going to have one observation split across multiple rows, right? So the idea is, if each observation or each case is a person, all of that person's information is within one row, okay? And you don't want to have two different people in the same row. You don't want to have one person's information across multiple rows, right? So, you might think about like, I don't know, but basically, your information should just kind of be in one thing. And if that's how you're going to structure your data, then that means each variable should get its own column, okay? And likewise, a column is going to contain only one variable, and one variable is contained all within one column. So you don't want to have a variable split across multiple columns, and you don't want to have different variables contained within one column. And then every cell is then going to be a single value. Okay. I guess there are some slight exceptions to this. Every cell is a single value. It is possible to contain little lists within a cell, but or vectors within a cell. But that's kind of a special case. So we'll just kind of keep it simple right now. So here's an example of, and again, I apologize for the screen over here, but and I don't know, maybe did you guys just have the PDF open on your own computer? Is that working there? Okay. So on this slide, this is an Excel file where we have some information. This was, I guess, looking at a general election from 2013 in Minneapolis, and we have different rows here. And so row 6 was Ward 1, Precinct 1, and so on and so forth. And then you have these Ward 1 subtotals and Ward 2 subtotal on line 15 and line 27. And those rows do not correspond to a single observation, right? Those are kind of totals of the previous 9 or 10 rows or something like that. Okay, so if you were to import this data set directly into R, this would not be a tidy data set because each row represents different things. Some rows represent just kind of one precinct within a ward, which is fine, and most of the rows are kind of like that. But some of the rows represent entire wards, right? Which consist of multiple precincts, right? And so in that case, your data, you have kind of a mix of different kinds of observations, represented in the rows, and so that makes it messy to kind of work with. And so if you were to try to total things up, you have to, basically, you have to, be careful, and things are going to get messed up. So, so we don't want to, so we would want to eliminate rows like row 15 and row 27 before we import this into R. Okay. As we look at variables, it's important to kind of just talk about the different kinds of variables that we might encounter. And broadly speaking, the two main types of variables that you're going to encounter are categorical variables and quantitative or numeric variables. Okay? Categorical variables record the type or the category. They often take the form of a word. So it'll be something like a person's hair color. Okay? And we're going to say this person has blonde hair, or this person has black hair, or this person has brown hair, or something like that. That's a category, okay? You have quantitative or numeric variables. These record some kind of numeric attribute and tell us a quantity, like how much or how many. So this could be something like, how many siblings does a person have? And their answer could be, I have 0 siblings, I have 3 siblings, I have 1 sibling, something like that, okay? Or it could be, what is somebody's height, or what is somebody's weight, or, how much money do they have in their bank right now, okay? And these are quantities. And when you have quantities, you can make comparisons. You can say this person is 5'10" and this person is 5'7". There's a difference of 3 inches between these two people. This person has $100, this person has $800. There's a difference of $700 between the people, okay? Certain things look like numbers, but they're not numbers, okay? So variables like zip code, area code look like numbers, but those are actually categorical, okay? So the area code does not correspond, like if you think of the area code of your phone number, does not correspond to a number or quantity. So if somebody says, Joe has area code 818, Jane has area code 562, it does not make sense to say Joe has, 250 more area code than Jane, okay? That's not a comparison that makes sense, right? Because these are not quantities, right? And even the way we read it, right? When you say area code 818, almost suggests that it's not even a number, right? If it was a number, we'd say 818, right? that your value is 818, your value is 562, and then you can do, subtraction and stuff like that. But in this case, they're not, right? Same thing with kind of zip codes and any other kind of thing that gets coded as a thing, right? Technically, there's also other kinds of variables. There's something called an ordinal variable, which is something in between a categorical and a quantitative variable. Ordinal variables have a natural order, but not some kind of number associated with them. So for example, if we're talking about clothing sizes, you have small, medium, large, and there is a natural order where you can say, large is bigger than medium, medium's bigger than small, and you can extend it to extra large, double XL, and extra small and things like that. And there's a natural order, but then when you say, okay, what number should we give to small and what number should we give to large, there's not going to be universal agreement or something like that. Okay, things like how strongly do you agree, right? I strongly disagree, I somewhat disagree, neither disagree nor agree, I somewhat agree, I strongly agree, or something like that. That would be an ordinal thing. What is it? Always, sometimes, rarely, never, or something like that. Those would also be ordinal variables, but again, not an objective number that you can assign to those things. Okay, and then there's another thing, text variables. We often treat text variables kind of like categorical, but text variables will basically contain text, and that text is not restricted to certain categories. So it could be like a free response. You say, give me your thoughts, and people enter text. And analysis of text data require text processing tools, and I would say that's kind of beyond the scope of our course. It is a fascinating topic, and there's a lot of kind of rich and interesting things that can be done, but you would need to take an entire course just on handling text. So if you are interested in working with text data for basically in your final project and things like that, you might have a data set that does contain a text column. I would say make sure your data contains other columns that aren't text, because that's going to be easier to kind of work with. And then if there is a text column that you do want to try to work with, you can come talk to me, and I can kind of give you at least some basic tools for working with text data. But again, if you want to work with text data, you'd probably need to take a full course on all of the different kind of things that can be done. But interesting stuff. Just a little bit, for an intro class, it's a little bit above our pay grade here. Okay, so just going on a little bit more about categorical variables. Most of the time we record categorical variables with kind of the word. So again, if we're talking about hair color, we'd say brown hair, black hair, blonde hair, red hair, other color hair, whatever, gray hair or something like that, okay? Sometimes we code the categorical variables with numbers. And so we might say, brown hair, we're going to write category 1, and black hair, category 2, blonde hair, category 3, or something like that. And again, just like the area code and zip code and things like that, if you do something like this, those numbers don't actually represent numbers or numeric quantities. They represent categories. And so you have to treat them as categories. You don't want to say hair category 3 is 2 more than hair category 1 or something like that, because it doesn't make sense, okay? And so I put this in bold letters, okay? It is a very big mistake to treat numeric codes for categorical variables like numeric values, right? So if you were to code hair category as a number and then calculate something like the mean, that's a very big mistake, all right? And I would say that's a huge point deduction if you were to do something like that in your project. And so, when you look at your data sets, this is something you need to be aware of, right? You're going to have columns. So again, depending on where you get your data, some of your columns might look like numbers, but if those numbers correspond to categories, treat them like categories and don't treat them as numbers. And I will be upset if you calculate the mean or something like as if you were treating them with numbers, okay? Also, on the other hand, there could be numeric variables that get turned into categorical ones. So for example, you could take someone's age, which we often think, if somebody says, hey, what is your age? your kind of default response, I think, is going to be to return a number. All right. But you could take something like age and turn it into a category. You can say, legally this person is a minor, legally this person's an adult, or you could say, this person is, Gen Z versus millennial versus Gen X, right? We're taking age and we're turning it into a category. All right. So, and there's probably some debate about what the cutoff lines are between, Gen Z and millennial. I don't know what would you say is the age between those categories and stuff. I don't know. But you're basically saying, okay, if you're between this age and this age, you're going to be categorized in this generation. If you're in this age and this age, you're going to be categorized in the other generation or something like that. Okay. Also, depending on your scenario, depending on your data set, what exactly counts as an observational unit could vary. And so, this is something you have to think about. And in some scenarios, maybe you want to treat, I don't know, one thing as observational units. In another case, you might want to treat observational unit as something else. Okay. And so, for tidy data, you want to make sure each table contains only one kind of observation. So, we looked at that election table, and you could have tidy data where each row represents the entire ward, and you'd have all of Ward 1, all of Ward 2, all of Ward 3 of the city. Okay, and then you could have a different table that has each precinct within the ward. So it'd be like Ward 1, Precinct 1, Ward 2, Ward 1, Precinct 2, and so on and so forth. And as long as you kind of keep those tables separate, you have a table of just wards, a table of ward precinct kind of things, that would count as tidy data. But if you mix the two, then it's no longer tidy. Okay, let me go ahead and give you your first view quiz answer. First view quiz answer for week 4 Wednesday is the letter D. D as in dog. D as in dog is your first view quiz answer. Okay, so here, each row here is a precinct within a ward, and so that it will be, this would count as tidy, all right? Each row represents one observational unit, which is a ward precinct or a precinct within a ward, and you would need kind of both of those things to uniquely identify a row, but that's fine, okay? And you can say, all right, there are 200, 91 voters or something, I don't know. Okay, so this is what we have, and that's what we have there. Okay, here is a different table. Okay, and in this table, each row, I don't know what just happened there. Okay, each row represents a different ballot that was cast. Okay, and so here it says this ballot was cast in precinct 04, and basically they left the ballot blank. Okay, and then the second row is a ballot in precinct P06, and these were the votes that they cast. And I guess you can cast 3 choices for mayor, and they cast 2, and then they left the third choice blank. So precinct 06, Ward 10. Okay. I don't know what's going on with the audio, but that's okay. Whatever. Okay. All right. Here, okay, you can't see, but if you're looking on your computer, on this thing, we have this is an excerpt of runner's performance over a 10-mile race. And what is the observational unit? So look at each row. The first row says Jane Polanek, 1974, sex F, age 32, year 2006, gun 114.5. And then we have Jane Poole, 1948, F, 55, 2003, 92.7. Jane Poole, 1948, F, 56, 2004, 87.3. Jane Poole, 1948, F, 57, 2005, 85.0. Okay, what does each row represent? What would you say?
Every row besides the last one represents who they are as a person.
Each row represents a person. Even the last one represents a person, but it's beyond just a person. It's more specific than a person. What is it? Yeah.
It's their performance like over time.
It's their performance within a specific year. Okay, so this tracks, I guess, a bunch of different people's kind of race times over the course of many years. And so this second row that says Jane Poole 1948 F55 2003 is Jane Poole, who was born in 1948. What was her race time in the year 2003? And Jane Poole apparently likes to do this race every single year. Okay, so she did it in 2003, she did it in 2004, she did it in 2005, 2006, and 2007. Each of those had different race times. Each year, her age went up by a number. Okay, and so this is Jane Poole's specific performance in the year 2003. The next row, Jane Poole's specific performance in the year 2004. And all of those things are contained in this table. Okay, so each observational unit here would be an individual within a specific year, that kind of combination. Okay, and we have, why do you think there is name year of birth in this thing? Because there could be two different Jane Pooles. There could be a Jane Poole born in 1948 and maybe a Jane Poole born in 1985 or something like that, okay, or 2002. Who knows? That's we have that, and I guess this is kind of under the assumption that you don't have two people with the same name born in the same year, but you know there could be two Jane Poole 1948s, and then you would probably need to have some other way to identify and designate things like that. Okay. So anyway, it's important for us to think about what each row should be, okay, or what each row is, and sometimes we want to reshape our data, okay? So here's an example where each row represents an observational unit, and we're kind of happy with this. So this is a storms table. So, you know, whenever there's a hurricane or a tropical storm or a typhoon, you know, some kind of weather phenomenon like that, we give them names, and then we measure things like the wind speed, the air pressure, the date that it kind of, you know, first it gets categorized and things like that. And so here's some information on some storms, and this is what we have. Okay, Alberto, wind speed 110, pressure 1007, date, you know, August 12, 2000. And so our four different variables are the name of the storm, the wind speed measured in miles per hour, the air pressure, which I think is in millibars or something, and then the date. Okay, and that's fine. Here is another table, and depending on how you might look at it, each case, each value that we look at, we might want to have that as kind of its own case. And so how is this table structured? It's structured a little bit different, all right? Oh gosh, this is really freaking me out. And so here we have three different variables, but they're not, each variable doesn't get its own column. So one variable is, you know, which country are we talking about? Another variable is what year did we record the data? And then the third variable is the count of cases, which would be, I think they're measuring like how many cases of some disease happened that year. So it's like, you know, in France in the year 2011, there were 7,000 cases. In France in the year 2012, there were 6,900 cases. In France in the year 2013, there were 7,000 cases, and so on and so forth. Except the way it's arranged is they're not, each variable, the three variables that we have, the country, the year, and the count, don't get its own column. They're kind of arranged this way, and so we would want to pivot this data. Okay, here's another table, and what are the variables we have? So currently the variables specified are the city the particle size and the amount of kind of pollution of that particular particle, right? And this is one way to arrange it. Someone could say, you know what, I want different the variables that I'm interested in is I want the city, I want the number of large particles as one variable, and I want the number of small particles as another variable. And in that case, the amount of large particles and the amount of small particles are contained within one column. So now, remember, when we have tidy data, each row gets its own observation. Each column contains one variable. And here we have basically two variables stored within the same column. The amount of large particles, the amount of small particles are both stored within the same column. And so we could pivot the data here as well, okay? And so the tools that we're going to use are, we're going to have, pivot wider, pivot longer, and things like that. Okay, I'm going to read in the data. These data tables are available just online, and so I'm using read_CSV. I'm just putting in the URL of these CSV files to kind of read in the data. Okay, one reason why we want to have each variable in its own column is we can do what we call vectorized operations. So I can say, basically I can mutate, I can run mutate, okay? Or here I'm just kind of manually doing this, but I could have done mutate storms and said, I want to create a new variable called ratio where I'm taking the pressure and I'm dividing by the wind speed, okay? So I would do, 1007 divided by 110 is equal to 9.15, okay? So this I kind of manually did. I could have used mutate to do this. 1009 divided by 45 is 22.4. And when you can use mutate, or you can do this kind of mathematical operation, and it's going to do it for each row. It's going to take the number in the first row, do your computation, and give you a value. It's going to do it for the second row, do your computation, calculate the value, which is nice. You don't have to write a loop to say start in the first row and do this, and start in the next row, go to the next row and do this, or something like that, okay? We haven't even talked about writing loops, but it could be something that could be useful, but again, you could avoid that kind of work. You can just say, hey, take this column, take the values in this column, do something with the values in this column, combine them, divide them, multiply them, whatever you need to do, and it will do it for each row, okay? Let's look at this cases table, and we could leave it like this, and we could do certain operations like, what's the difference between 2012 and the difference between 2011, and that would be fine. We would want to leave it in this structure if we wanted to say, hey, how did it change from 2011 to 2012? All right, but there might be another situation where perhaps you have, let's say this is one table where we have cases of, disease A, right? And then you also have, let's say you have another table, cases of disease B, okay? And you want to compare how prevalent was disease A versus disease B in the year 2011 for France, okay? This table structure doesn't allow us to do something like that, okay? And so what we would need to do is we need to pivot the data in this table. So we have in France in 2011, these were the number of cases of disease A, okay? And then perhaps we have a different table and we'd say in France in 2011, these are the number of cases in disease B, and then we could do, a join operation, join on country and year, and then combine these, different things. So again, applications coming in the future, but we'll do that, okay? So anyway, how would we want to, if we want to restructure this, okay, and we want to say each row is going to be a country and the year and the number of count, how many resulting rows will we have in our resulting table? If I restructure or if I pivot my data, how many rows will we end up having? 9. We're going to have 9 rows, right? Because we got France 2011, France 2012, France 2013. We're going to have DE, which is Germany, Deutschland, not Denmark or something, okay? Germany in 2011, Germany in 2012, Germany in 2013. Okay, US 2011, US 2012, US 2013. We're going to have 9 9 rows. Okay, well here it says France 2011, Germany 2011, US 2011, or something like that. Okay, so we're gonna have 9 rows, and we have a column for country, a column for year, a column for the count here. Okay, should I just turn off my? Am I better off just? Can you guys hear me just fine? Okay, we'll just turn off the mic. Okay, none of this robo speak here. Okay, so to do something like that, the function we're going to use is called pivot longer. Okay, and we call it pivot longer because basically we start off with 3 rows and we end up with a longer table, a table with 9 rows. And what we're going to do is we're going to kind of gather. Okay, we're going to take these 3 columns and we're going to combine the numbers into one column, right? So these numbers, 7,000, 5,800, 15,000, kind of get combined into just one column of values. And so when we do pivot longer, we're going to say the columns that we're going to kind of combine into one column, we specify we're going to combine the columns 2011 through 2013. When you do that, okay, it's going to default to just names and case n, but you can or value, but you can kind of specify the name of the columns that you want to do. So here we took these values, and here we called it year and n. But we're going to say, all right, take the names, okay, the column names, which are 2011, 2012, and 2013. Those get combined into their own column. That column is called the names column, right? The names of the columns go to the column year, and then the values go to the column cases, right? And so, so here we have France 2011 had 7,000 cases. France 2012 had 6,900 cases. France 2013 had 7,000 cases. Okay, and so the values here again get combined into a single column. So just a little bit more detail on this. Columns are the names of the columns that are going to get pivoted. In this case, we want to pivot the columns named 2011 through 2013. And here you can kind of specify multiple columns using the colon operator, which basically says from column 2011 through 2013. You can also provide a vector, so you can do C parentheses, 2011, comma 2012, comma 2013, or whatever columns else you want to pivot. Names 2 is a character string that will tell you what it's basically the name of the column where the names go to, and then values 2 is going to be what's the column that contains the value. Okay, those names are arbitrary, so it makes sense to use the name year and cases, but these are just arbitrary values. So if I wanted to call it names to the column called when it happened, and values to, we're going to call that column how many, R is going to accept that. This is not good practice. You don't want to have spaces in your column names, and you don't want to have overly long names. But again, they're arbitrary, and you can kind of specify whatever you want to call those columns. So again, previously we said year and cases. I think that makes sense. But again, if you wanted to be kind of cheeky and use some kind of name here, other names, that's also fine. It's going to do the same operation. Just call your columns something else. Okay, I'm going to ask you this question. Let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat is our second view quiz answer. Okay, what happens if I only pivot the columns 2012 and 2013? So here I'm going to say pivot this table longer. We're going to pivot the cases table longer. And I'm going to pivot the columns 2012 and 2013. So how many rows will I end up having? Yeah, we're going to have 6 rows, okay? And what happens to the other columns? What other columns will I have? So the columns 2012 and 2013 get pivoted. So we're going to end up having 6 rows. And the column headings 2012 and 2013 end up in the column called year, and the values inside the columns 2012 and 2013 end up in the column called cases. All right, so that's what we have. The columns that did not get pivoted get repeated. All right, and so that includes the column 2011. All right, the country name and the column that didn't get pivoted, so country and 2011, just get repeated. So it's going to say France 7,000, France 7,000, and then 2012. So this feels a little confusing because this column, we feel like 2011 should have been pivoted, and I agree, 2011 should have been pivoted, but R doesn't have any kind of context and understand any meaning of these things, so it's just going to say, oh, these are the columns you want to pivot, I'll do it, and anything that doesn't get pivoted, it's just going to repeat. Okay, so you could imagine perhaps more information was in the table, like I don't know, this capital of each country or something like that. Well, that's going to get repeated as well. So any column that doesn't get pivoted will get repeated. What if I try to pivot all the columns? So I'm going to pivot country, 2011, 2012, and 2013. I'm going to pivot all 4 columns. What's going to happen here? How many rows will I end up having? Okay, there's 12 values total, and all 12 values, because all 4 columns are going to get pivoted, we're going to end up with 12 rows. Okay, the names, we're going to pivot to the column name. The values are going to get pivoted to the column value. Actually, if you try to do this, you're going to run into an error, because it's going to say, hey, you've got numbers over here and you have characters over here, and I don't like trying to combine numbers and characters. So first it's going to say, I can't combine character and double kind of meaning numbers. Okay, so first you're going to get an error. Now you can kind of force it, and you can say, you know what, just do it anyway. We're going to turn everything into characters, and now you can combine the table. All right, or now you can pivot the table. And if you kind of force it that way and you say, okay, turn everything as a character and then pivot, yeah, what do you get? You end up getting 12 rows, 1 column of names, 1 column of values. And basically it's kind of like, almost it's like instructions for like each cell in this table, right? In the country column, we had France, and in the 2011 column, we had 7,000. In the 2012 column, we had 6,900, and that's kind of what we're saying, okay? So it's kind of like all 12 values get their own row here, right? Not a great thing to do. So, obviously, when you pivot the data, you want to pivot the correct columns. But again, internally, R will just do what you ask it to do, okay? Okay, here's the other example. We said, we had this pollution table, and we had the values. We had the number of large particles and the number of small particles all within the same column. And so this time, we want to create a column of just large particles. We want to create a column of just small particles. How do we do something like this? Well, we're going to do the inverse operation, all right? So earlier we had pivot longer. What do you think the inverse operation we would call? Here it's called pivot wider, okay? We're going to pivot our data wider. We're going to take the values within one column, and we're going to say, okay, we have multiple columns of values in this one column, and we want to kind of pivot those across multiple columns. We're going to pivot our data wider. Okay, so this is what we want to do. Is if we start off with these 6 rows, and this column has 2 variables in it, we want to kind of pivot our data wider so that we have one row for New York, the number of large particles, and the number of small particles. A row for London with the number of large particles, number of small particles. A row for Beijing, number of large particles, and number of small particles. Okay, so does this operation kind of make sense when we're going to say we're going to take the values in one column and pivot them wider across multiple columns? Okay, I hope that makes sense. So in this case, the function we're going to use is pivot wider. We're going to pivot wider our pollution table. Okay, and again, with dplyr, you could have done pollution piped into pivot wider. Okay, and we are going to say the names of the columns, the new names, of the columns, right? This column large and the column small. The names of these columns come from the column's size. Okay, so we're going to look at the size column, and we're going to take the names out of that. And then the values that go into these columns are going to come from the column called amount. Okay? So that's how we do it. So we say the names come from the size column, and the names are large and small. The values come from the amount column, and those values are, you know, these values: 23, 22, 121, 14, 16, 56. Okay, so again, pivot wider, names from is the name of the column that has the names that will become column headers. Values from is the name of the column that has the values that you want to pivot. Pivot wider is very sensitive to spelling differences. So if we have our table, if our original table looks like this, all right? So we have, instead of New York, we have NYC. NYC large 23, New York small 14, London large 22, London small 16. If I pivot this wider, you know, again, the computer doesn't have any kind of context. It doesn't know that NYC and New York represent the same place. And it just sees, okay, these things are spelled differently, so they're different values, okay? And so when we pivot this wider, how many rows are we going to have? We're going to end up with 4 rows. We're going to end up with a row for NYC, a row for New York, a row for London, and a row for Beijing, because it sees New York and NYC as different things. When it pivots it wider, it's going to say, okay, I found a value for NYC large, 23, but I didn't find a value for NYC small. So it's going to put in an NA. It's going to say, I found a value for New York small, 14. I didn't find a value for New York large, so it puts in an NA. Okay, London, it finds both the large and the small, 22 and 16. Beijing, it finds both large and small, 121 and 56. So it populates those things. But things where it couldn't find them, it's going to put in an NA. Okay, sometimes you don't want to have the NA. Sometimes you want to put in a value. You can say values fill. If it basically says, you know, you can put in a 0 or something like that. You got to be careful. I would say this leads to incorrect values, right? Because it's not that NYC had 0 small particles, right? Right. That's actually not correct. So in some cases it makes sense to put in a value like 0 or a value, you know, some other default value. And in other cases, like, no, that's wrong. All right. Like, we don't want to say New York City, NYC had 0 small particles and New York had 0 large particles. So kind of populating the values in this way, I would say, is actually incorrect and wrong. And you should just leave them as NAs. But again, depending on the situation that you're in, maybe it makes sense to fill it in, and that option is available. Okay. Again, here's another case where we have, you know, just a spelling difference. Okay, and again, R is case sensitive. So here I've replaced, I have all caps large. You know, as far as the size of particles, I got all caps large. I've got small, large, small, large, small. All of those are all lowercase. And here, if I say I want to pivot this wider, and the names of the columns come from the size column, we're going to end up with 3 columns. We're going to end up with a column for all caps large, a column for lowercase small, a column for lowercase large. Okay, because those are the kind of we have 3 unique values in the size column, so we're going to end up with 3 columns. And so when you do it like this, it's going to say, okay, I got NAs for New York lowercase large, and then I've got NAs for London all caps large, NA for Beijing all caps large. Okay, so R is just going to pivot your data as you asked, and it's going to create columns based on kind of unique spellings. It's going to create rows based on unique spellings of kind of the rows there. Pivot longer and pivot wider are inverse operations. So, you know, we saw this operation going from this table with 6 rows down to a table with 3 rows and 2 columns for the particle size. Okay, but you know, you might have data like this, and you want to pivot them longer. Okay, so you could take this and you can do pivot longer, and it's going to kind of pivot the two columns into one. So they're inverse operations, okay? Again, here we did something like this with the cases table, and we pivoted them longer. If we want to take this and pivot them wider, we could, right? And so again, each of these things require a little bit of just kind of thinking, what is my observational unit, all right? So here, your observational unit in the longer table is each country and the year, and how the values are how many cases. And this top table, before we pivoted longer, the pivoted wider version, each observational unit is just a country, and we have columns for each value. So this top version is great if you wanted to say, okay, how many, what is the change of the number of cases from year over year? We can compare 2011 to 2012, 2012 to 2013, right? Because you can compare the values across that way. This would be great if you had, again, like a second table that you wanted to combine. One table has how many cases do we have of disease A? How many cases do we have of disease B? Or something like that, right? So you could imagine, what was it? Coronavirus, I don't know, what were the different variants? You had like Delta, right? And then coronavirus, Omicron, coronavirus, I forget all of the different variants that we've had, but you might want to say, okay, how have the number of cases changed across, over, each row or each month or something like that. And so, again, depending on what operation you want to do, you have these tools to kind of restructure your data so you can do that, right? So again, I'm just giving you a whole bunch of different tools that you can use. And then, how you apply it, how you use it, that's up to you. So there's lots of functions and availability there. Okay, last view quiz answer for today is the letter A. A as in apple. A as in apple is your final view quiz answer for today. And we will go ahead and end here, and we will see you on Friday.